Hello community, so great that you are back. Yes, today we talk about the latest development in RAG for Code AI. So, you remember it was the end of October 2024 and there was this idea for the software development, hey, do we really need this complex autonomous software agent? What we built something, we called agentless. And it was a beautiful idea. It has 3 phases and it says we localize the error, we just repair the code, we have a patch validation and on we go. We don't need complex tools or anything at all. And you know what? It immediately had the highest performance overall. So this was great, but this was 2024. Now at end of June 2025, we have Software Bench, Software Engineering Benchmark, generating also patches to fix our issues in complex code bases. But if we look now here, and I look at the open source system, we have here Software Agent and Claude 3.7 Sonnet, 4 Sonnet, and the best one is currently RACG agent. Absolutely beautiful here in the light version. Please note light version. And I just checked it here, RACG. This is here, it is open source, you can use it. And they have here the tool use and they tell, hey, you are an agent, an autonomous bot for coding task. There is the strategy. So we hard code the strategy. Step 1, gather the existing knowledge. Step 2, gather the context of the query, understand as much as you can from the environment. Step 3, make a clear plan how to propose to go forward to try to solve this. Step 4, make changes step by step. Just step 5, check and improve your work, self-reflection, everything that you know. And I think currently they're using the multi-agent system. For the strategy itself, I think they currently use an O4 Mini from OpenAI. And then for the agent, the orchestration agent, I think they use a Claude 3.7 Sonnet or already switched to a Claude 4 Sonnet, I don't know. But you see, this is a beautiful combination and RACG is currently #1 in the open source on SWE Bench Lite. If we go here to the full version, yes, you have the professional models from Amazon and Atlassian. But this is now interesting. What we are interested today is that there is a difference if we have our RAG text retriever and our code retriever. And the new research tells us, hey, you know what? Those code retriever, they are underexplored because everybody believes they are a text retriever. Now, this would be a big mistake. Now, unlike the text documents, the semantic meaning of a code snippet can be completely modified just by a small syntactic change. Exchange a plus and a minus sign or shift a comma somewhere. Making traditional retrieval analysis less effective for the code search task. So interesting, Carnegie Mellon University tells us, hey, we had this idea, there's a difference, and those code AI systems, you know what? We evaluate them. So there's a new research and they say what we found is state-of-the-art code retrievers, if you want for RAG system for code, are not as smart as we think. So another hard limitation for our code AI systems. AI is not perfect yet, end of June 25. Therefore, and they say humans are easily fooled by superficial prettiness and also the AI are fooled by the superficial prettiness, like a good comment or a variable name that is a kind of a sexy variable name. And often the AI system failed to grasp the deeper functional logic of the pure code. And this is a statement that is quite heavy. When I read here this publication, I said, I have to show you that if you thought code is perfect, Cursor and Sonnet, and this is the perfect combination for a code editor, and so on. No, we still have massive limitation for mission-critical task also in our code AI. And they went on and they said, hey, the new research here revealed we have a massive bottleneck for creating truly intelligent AI developer tools, especially for code generators. Here you have now the study by Carnegie Mellon University published June 25, 2025, Understanding and Combating Textual Bias in Code Retrieval with a Semantic-Augmented Reranking and a Localization. And you might say, that sounds familiar. Yes, of course, it is the little brother of our classical RAG system, our multi-agent reasoning RAG, and it is called RACG, Retrieval-Augmented Code Generation. So whenever you have your LLM and it doesn't know anymore how to write code, it goes out to the world, and maybe overnight there was an update in the GitHub repos for some particular topic. We have new code available, and we have simple a RAG procedure, multi-agent reasoning RAG procedure, of course, to import now new code. And what they found is simply amazing. Now, the beauty and why I show you the study is they did not only find problems, they did not only find that it is not working, but they also proposed here a solution. So let's start. Researcher asked you two simple questions. Hey, what features are code retrievers really looking at if they try to find the right code sequence for my task? And the second one was, are those code retrievers, are those code AI systems in any way biased? And what a surprise, the answer is absolutely. So what they did, they designed an experiment, as always in physics, no? And they call it a normalization. And the idea is simple, honestly. You just systematically strip away the textual information from the code while keeping its absolute functional, absolutely identical. The code is working. Think of it as taking here a well-commented function and renaming everything just with generic placeholders. The code works. Let's say this is my original code and I have here this simple definition. And now the normalized code would exactly look like this. You see? I have not defined my function summation to numbers, and I have not written calculate the sum of all integers from 0 to n equal numbers inclusive. I just have given the pure code. And for a code LLM that understands pure code, you might guess, perfect, this is all it needs. No? This is an operational code. This is pure code. Now guess what? Also the functions do exactly the same thing. One is textually rich, and let's say the other is textually really poor. Yeah? And the setup was chosen in this particular way for a reason. Because they wanted to isolate here the semantic understanding here from the as you see here in blue, the description here of the text code, the textual description, from the real textual pattern matching of pure code notation. And you know what they found? And I give you the result. You find all the nitty-gritty and all the sub-result in the paper. What they found was the following. When they tested here the code retrievers against the corpus of normalized code, the performance of code AI collapsed. And if I say collapsed, I really mean collapsed. Have a look at this. And this here is a screenshot from the paper. And they have here the original function. And again, it's the same function I showed you before. We have here beautiful, yes, calculate the sum of all integers from 0 to a particular number inclusive. Beautiful. And then we have it normalized. So if you want, the text is reduced. And all the number here, the parameters, are now simple variable 0. It's absolutely consistent. It's a functional code. But guess what? When they did a retrieval recall at 1, their performance was 99%. But when they used the normalized function and they were looking for the code, the retrieval recall at 1 was 9%. Now, just to show you, this is the performance difference between normalized and non-normalized. Here, okay, 98.6, I wrote 99. This is the performance we have with this kind of code. And this is the performance if you give a code AI just the code. And you might say, this is a little bit strange, no? Because the code AI understanding code should immediately, the best, the biggest AI models in the world on this planet, they are not able to understand that this is identical. Beautiful. And it shows, tell us here, Carnegie Mellon University researchers, that current code retrievers, despite being trained on code, billions and trillions of tokens of code, behave still like simple text search engines. So they heavily rely on matching the words in my query, in my human query, when I say or have something, with the identifier names and the doc strings in the code itself, rather than really understanding the underlying logic of the code. So code AI fails on understanding the logic of code. I think this is a statement that you have really to enjoy. And then they did a test here, an asymmetric test. And they say, this is not possible. This must be a mistake. No? It is so great. We write code to build a web page every day. Everything for this simple task, everything is working. No? And they said, so let's do something, an asymmetric test. And for a given query, they took here the one correct code snippet that was working, that was presenting the ground truth for the golden example, and they normalized it. And a lot of other code candidates that were not working, that were incorrect candidates, but they added original, well-documented, pretty forms and explanation. But remember, the most important fact is non-working code. And then they said, okay, my little LLM, you are looking for new code. You don't know inherently how to solve this code example. Here you have a database full of code, 1,000 GitHubs. Go and find, retrieve here in a code rack, retrieve your code. And you know the result? The retrieval performance got even worse. You know why? Because it was not understanding the code that it needs. It was just looking at the textual description that was somewhere intermingled in the code. I think it's amazing now, at the end of June 25, we are understanding that the code AI are not working on code, but on the text between the code. And here you have now their results in detail in a tabular form, and they tell us the result demonstrates that when only the ground truth document is normalized, so here the S2 normalize the ground truth, and the others incorrect stay the same, the ground truth documents rank, the correct document rank, deteriorates dramatically to 288 compared to when all documents are normalized. This is here the S1 case. So if you normalize everything, the incorrect and the correct case, okay, it's real down. But if you normalize only the correct, then you leave the other here with the beautiful textual code and with the textual description of the code and the non-operative code example. Yeah, the average rank just crumbles down. And you see this on multiple embedding model here, OpenAI. So they checked it, and this is a general behavior. And now Carnegie Mellon tells us, we think this reveals a strong and a dangerous inductive bias of code AI. Because the model has learned one rule, that well-documented code is the good code. And this is the code that I, as an AI system, will use for my user to answer the query. And when faced with a choice between the poorly documented correct code answer and a well-documented incorrect code answer, it will overwhelmingly prefer the wrong one, the incorrect code sequence. And it will learn the incorrect code sequence, and it will reply and apply the incorrect code sequence to your task. This is the performance of current AI system. And Carnegie Mellon tells us, we think this is a critical failure mode for any automated system relying on retrieval, in our case, code retrieval. So this is the state of AI at the end of June 25, and I have to tell you, I was kind of amazed at this study because I believed, at least in coding at Python, C++, our AI are pattern machines, no? They understand the code patterns. And now it turns out they don't understand the code patterns, they just understand the textual description that is intermingled in the code sequence, but not the code itself. So Carnegie told us a solution, and they said it's easy, no? We take the weakness and we work with this weakness and we make it strong. And they said, if code AI is biased in this extreme way to textual description of code, then let us use that bias to our advantage. And yes, you got it. This is exactly what they did. So they invented now this Semantic-Augmented Code Reranking and Localization methodology called SACL. And they said the core idea is to generate high quality, semantically rich textual description for the code. And then we use those descriptions to improve the code retrieval, because finally the code has a text description that was syntactically generated by an LLM. And we just hope that the LLM got it right, because otherwise we have a problem, because this is a syntactic cycle of data generation and data augmentation. And my goodness, this will be fun. So here you have it now in a short visualization. So we have here on the left side, the Semantic-Augmented Code Reranking. And on the right side, we have the Semantic-Augmented in-context localization. I would like to explain this now for the next 2 minutes, that we really understand here this new methodology, where they say maybe we can counteract here because we cannot train Sonnet 4 new. It's too expensive for university, no? So, okay, step 1, the left side. So they say, okay, the documents are retrieved based on the query similarity, then augmented with the generated description, and the final ranking score are combined now. And we do not only have the code query similarity score, but now that we have added a textual description, we can do a description query similarity score to improve the retrieved performance. Beautiful. This was a little bit too fast, never mind. 3 simple steps. At first, the initial retrieval with the biased model. Ne? We have the standard retriever to get here the top K, top 100, top 1000 candidates. I use 1000 for the code snippets, especially in the textual. It's good if you go to 1000. I have even seen the description going up to 2000 candidates if you have your search in the vector space. So you know that this list here is biased because this is the classical code AI. This is the classical retriever for code segments. And then we do here the intelligent sync. We have a semantic augmentation. So we use now an additional LLM. So for each retrieved code snippet, and please remember, for each retrieved code snippet, 1000 or 2000 of them, use now an LLM. CMU used a Llama 3.1 8B to generate now a natural language description of the code functionality and of the code purpose, as good as a Llama 3.1 understood it. So then we have the code, then we have the text, and now we go in the vector space and we calculate the similarity score for text to code and text to description. And then we just add the code, we put them together and we get a new code. And this is, if you want, our re-ranking. Exactly do in the classical text RAG system, multi-agent. Now the second step is much more interesting because you don't know where all the code sequences are in a file tree. No? So the harder problem they tell us in a repo-level retrieval, so finding the right file to edit in a large project repo, is a simple file tree gives very little information about what each file does. And you say, no, you're not gonna. Yes, absolutely, this is what we're gonna do. Enhances this by augmenting the repo structure. So each and every single file, they open it up, they look an LLM chat and look at it. And then we generate here a summary for each file. Python, C++, whatever we have. We go through and for the 1000, 2000, 5000 retrieved segments or solution, we do this. And you say, yippee. So, example. Very easily, the agent sees now at this particular time step here an augmented file tree. No? Here, for example, here Python file. This Python file provides here a custom implementation of a particular algorithm, and we have the following parameters, and the following methodology is applied, and the result is compliable, and we have done a check, and blah, blah, blah. Great. So you see, those small descriptions provide now a crucial context about the rule, the purpose, and the key component of each file. And this now finally allows here in this new method, allows an LLM or an agent, the LLM is just in the brain of the agent, to make a much more informed decision about which file is related to a bug report, leading here to an improved fault localization. In theory, easy, but computationally, the hell on earth. The final verdict. I give you now the result. In the paper, it takes a long time. I just give you the final result. the improved retrieval up to 12.8%. The improved localization up to 8%. In overall, the better downstream code generation, the ultimate goal, why we do this, why we kind of hope to counteract here this massive limitation in code AI. If we do this, they have here on the human evaluation benchmark, they say this will lead to a 4.88% improvement in code generation. And Carnegie tells us, fixing here the retrieval bottleneck has a direct positive input on the final output, so we achieved an improvement of 5%. Okay, I mean 5% for everything we have to do. For me, this is the beginning of a solution, but not the final solution to the topic. If you want to have here much more detail here for the specific at 1, at 5, at 10, everything is here for you. Beautiful. The study is really good to have a lot of detailed data. Please have a look at itself. I'm just giving you here the idea and the result. There are a lot of steps in between. But in general, we can say this paper is really, I think, a beautiful study because it doesn't just present you the new method. At first, it does a diagnosis of the system. And it tells us, hey, we found a fundamental weakness in the current AI system for coding. And I think we should be aware because AI code is not perfect. And Carnegie Mellon tells us, hey, it exposes that our code retrieval model, Sonnet 4, whatever you go for, are often faking it. And I think this is an amazing statement here. And they say relying here only on shallow textual tricks rather than a deep understanding of code itself. So if you use here those systems to write your code, to help you write your code, to support you in writing your code, this is great. If you, as a human, you define the start, you know exactly what to do. For each and every other exercise, just be aware that in the pre-training here of the code AI system and structures, if there were, I don't know, 1 million GitHub repos that they trained on particular task, the well-documented code is the one that was learned. The non-well-documented code that might be the better code, the more elegant code, the more performant code, was not learned in your code AI system. Is it a final solution? I hope it is just the beginning. Let me end on a personal note, because this is fascinating. This shows us a general development we have currently in AI, no? It's a perfect case study, I think, of a more powerful trend, no? If some component in a multi-AI system fails, and we have multi-agent now, it's easy, no? The other fixed just the weakness of this one single agent that failed. But you know what? This agent has an LLM at its heart, at its brain, and this is a systematic failure. The other agent, it's simple to say, yeah, and then the other agents, they just compensate, no? They just calculate more. They just to need a little bit longer calculate everything, or they need a little bit more connectivity or whatever. It is a systemic failure that we encounter. And just think about the cost if you would now implement here this particular solution for extra LLM calls for every candidate document during the re-ranking process. Okay, maybe it's just 1,000, maybe it's just 2,000, but for every single code step. I mean, this cannot be the solution. No? And then there's something else. Because do you remember in the good old times here at the end of 2022, my goodness, there was something, I don't know if you remember, I called it hype, but it's called, of course, HYDE, the hypothetical document embeddings. And you remember what they did at the time? The idea was simple. Given here my complex query, I ask here an LLM to generate here a hypothetical ideal answer that the LLM would think is an answer. So the LLM does not try to understand my question, have a deep dive in strategy, goes out to the internet, explore everything connected with my query. No, the LLM says, this is the query, I think this would be the real answer. It might be the complete wrong answer, but this is not the point. Because now I take this ideal answer and I embed it in, let's say, a 1000-dimensional vector space. And in this vector space, we already have all the other solution, all the other code solution for a particular query. And you know what you do, and this was the idea of height, you take this ideal vector and given here the embedding of this vector in the vector space, you just look here around here in your close environment and you take everything over there because you hope that in your surrounding, in your direct environment, in your direct epsilon environment, there's also the vector with the real complex solution. Again, we operate here in a vector space with a semantical similar objective function. This was 2022, but you know, I see it now implemented on another level in our large language model, and in particular by the OpenAI models. Now that OpenAI have a knowledge what I like, what I prefer, about my complexity that I work in and my stupidity that I want the answers in a particular way, OpenAI knows me, and you know what's happening? A login. Because knowing now what I expect or what I validate or say this is the correct answer, I have a feeling sometimes the AI builds a bubble around me with the things that I like. That the AI has in its memory, hey, this particular user, 212, likes to have it presented in a particular way, likes a particular complexity, and it is responding in a way that I like here the answer and I like the reasoning path and I like the complexity. Call me crazy. I think AI is building a bubble around me that I'm a happy paying customer. Now, you know, the same is happening now with code because this was here about textual RAG. But with code retrieval, multi-agent reasoning retrieval, we have now the same, no? At first, the LLM writes a simple code version of what a function should look like to solve my query. And then we have an embedding of this newly synthesized, and you find in the vicinity a perfect answer vector that can be re-represented here in a pure code sequence. And then, given a massive code database, was recalculated here in this vector representation, we found an answer. But you know what this means? This means the AI is not thinking anymore about an answer. The AI goes with the simplest answer it can think of, puts this in a 1000-dimensional vector representation, and looks in the mathematical space of the vector space itself, just what are the closest vectors in my environment. And somewhere from the internet or the complete GitHub code base was encoded in a vector space, in a mathematical space. And now I'm just looking, hey, what vectors are close by to my vector? And this is the solution. I don't think about the conditions. I don't think about the relations in my query. I don't think about validations. I outsource the intelligence of the LLM to a configuration in a vector space, and I hope somebody else found the right answer and built here an embedded vector and put it in this particular vector space for everybody. Kind of a Wikipedia vector embedding space with all the answers. I'm not sure if I like this particular development. I understand for OpenAI and Microsoft it is great because they don't have to run their model. They say we have a solution space. We have an LLM, gets a query, generates here a very short ideal answer, and we just look here in the surrounding, take here the answers back, and we don't have to calculate, we don't have to reason, we don't have to argue, we don't have to think, we don't have to build reasoning traces, nothing. Quick, dirty, fast, done. Great profit maximization. But I don't know if this is the right way forward. And also, everything currently in AI, at least in my idea, everything falls back to one plane. the reasoning complexity that we have in large language model. If you look at robotic system, if you look at video system, if you look at a vision language encoder, if you look at whatever, everything is coming back to the reasoning ability of a large language model. Here's the central intelligence of all AI system. Independent if it's a single agent, a multi-agent system, a swarm AI intelligence, everything comes back to the reasoning in large language model. There's no other intelligence, or you outsource it into a vector space. I hope you had a little bit fun with this video. If you would like to see more, why not subscribe, and I see you in my next video.